Hello and good morning to whoever's watching this video, especially to my classmates from Engen ME221 Thermodynamics. This is our challenge number 2, part 2, number 1 given. So this is about the milk plant. So I will read the given, but I will also copy paste the given into the description of this video so you can follow along. I will only do the balancing of the equation as I am not prohibited to give you the answer. So yeah. So I'm gonna read the problem now. A milk processing plant uses an electrode boiler. So it is a boiler powered by electricity to supply saturated steam of 10 bar to heat up the milk from 6 degrees Celsius up to 95 degrees Celsius during our pasteurization. The milk is pasteurized at the rate of 13 liters per second, and the dairy plant operates for 6,200 hours a year. Our client wants to know how much electricity they will use per year for this heating process and how much it will cost if the electricity is 14 cents per kilowatt hour, and the efficiency of his electrode boiler is almost 97%. Take the density of the milk to be 1035 kilogram per meter cube. Okay, so I'm gonna explain our drawing or sketch here. So this is Mr. Colin. So this is our milk source. So Mr. Cow will give us some milk. Oh, let's just say this is a container. Container. It's gonna give us some milk, and it's gonna be passing through this box. We call it the heat exchanger. So it's full of pipes and coils usually. This is our boiler powered by electricity, and it's gonna send our 10 bar steam into our heat exchanger to heat up the milk, and it's gonna be going to come out of the heat exchanger with 95 degrees Celsius to kill all the whatever bacteria is in the milk or microorganisms that needs to get pasteurized. It's gonna go to the cooler, and now we have our moo milk in here. Okay, why do we have two red boxes? This one is CV1 or control volume 1, is this one is CV2 or control volume 2. Let's first focus on this one, heat exchanger. In the question, it only mentions that we are using the saturated steam to heat up our milk, but it did not define that we are going to mix them, which in real life we do not mix the steam to the milk. Why? Because it's gonna make your milk bland. It's gonna make contact with the milk, and that's no good. That's not good. And also, having that steam getting in contact with the milk, it means that we have to account both the amount of steam and the amount of milk that we have in the total system. Moreover, if we add the steam to the milk, we're gonna have more substance inside our container. So more volume means that it's gonna take more time to increase its temperature, and that's not very convenient to to our milk pasturers, if that's what you call them. So I have separated them into CV1 and CV2. So let's explain this one. In the boiler, the energy input is electrical work. But in here, by the time that it reaches the milk, it has been converted into heat because there's no electricity flowing from the boiler to the milk, only 10 bar of steam. If you use one box, your SFEE equation gets cluttered with both terms. It's gonna make things very easy to accidentally cancel the wrong one or double count the energy. So we will not be adding the heat to the electricity we're using, since it's just been converted. It's not gonna add up. Next one is efficiency trap. So we have the efficiency of 97 for our boiler, and that is a property of the boiler hardware. It's not the milk flow. If you use 1-bit box, it's much harder to see where that 0.97 is actually going in our problem. Next is property discontinuity. We are dealing with two different fluids. We're dealing with water and steam in here, and we're dealing with milk on this one. So a single control volume will force you to account for the mass and enthalpy of both simultaneously. Splitting them, let's solve for the demand, which is the milk, and the supply, which is the boiler. Okay, now let's do this thing step by step. So first we assume that our that everything in here is at a steady state. So we assume that everything is at a steady state. We also assume that there's no significant change in the height, so we're not gonna be applying any potential energy, and we're also considering that the milk is just flowing naturally through our pipe, since it wasn't mentioned in the problem that there's something injecting the milk into the system. So we're gonna be canceling out our gravity, and we will also be removing our KE, or kinetic energy equation. So now we will be also considering the milk density, which is P, which is 1035 kilogram per meter cube, and our specific heat, which is almost 3.89 kilojoule per kilogram Kelvin. And we consider this as an adiabatic boiler, meaning no heat loss from the boiler to the room, since it wasn't mentioned. So if it's not mentioned, we just assume that things are as is. So now we were left with the equation Q minus W dot is equal to mass flow rate enthalpy 2 minus enthalpy 1. So the logic in here is that we still have the W, we still have the Q, we still have the mass flow rate, and we still have the enthalpy. So this is gonna be our equation for now, but we're gonna be substituting some things. Okay, our work will become, so this one is for the CV1, our work will become 0. Why? Sorry. Our work will become 0 for the fact that there is no motor or no electrical elements that are inside this box touching the milk. It's just the pipes. Okay, the milk is running to the pipes, and the steam's getting pushed through the heat exchanger. They don't have any direct contact, and there's no piston, there's no shaft or whatever. Okay, so our work in here is 0. And for our enthalpy, since we were provided with the temperature earlier, which is we were provided with the temperature earlier, and also since this is a liquid, we can use our formula, our get-go formula, which is for a change in enthalpy, you can use specific heat and temperature. Okay, now we're gonna be computing things to solve it. So we need our mass flow rate. So to get that, we need to solve for the we need to grab the density and our given volumetric flow rate. And now you're supposed to be getting an answer in the form of kilograms per second, which is I'm not gonna be providing that. You have to solve it for yourself. Now we're gonna be getting our heat rate. So to get the heat rate or our QN, like how much heat we've put into the system, we will be using our new formula. So our new formula will be QN is equal to mass flow rate, which is the ones that you will be solving here, and we're gonna be multiplying that with the specific heat and the given T out minus Tn, and you're supposed to be getting an answer in the form of kilowatt per hour. Now we're gonna be moving to our CV2. So for the CV2, so for the utility side, for the box, for the boiler side, this will be our equation: Q minus W elect is equal to steam enthalpy out minus enthalpy in. So we're gonna be dissecting this again, okay? We assume that the boiler is insulated since it doesn't mention any loss in heat or whatever. So we assume that this one is 0. So the electrical work, which is the power from earlier, is the only sole source of our energy, steam's energy. And because the boiler is at 97% efficiency, we should be getting more electricity from the grid rather than the heat that will deliver to the milk. So our formula will be W electricity dot is equal to Q need over our efficiency. So our efficiency is 0.97. Our Q needed is the ones that we have solved earlier, so it's a kilowatt thing is equal to another kilowatt. Note that this should be higher than this because this is the 100% electricity that you're getting and this is the efficiency, so it's only working on its 97% capability. So we assume that the other 3% is lost in the system somehow, and which we won't be computing for that. So this will be your answer. And now we will be computing for the annual energy, okay? So for the annual energy, which is in kilowatt per hour, we will be using this answer, plug it in here, and you're gonna be multiplying it by how many hours since it's kilowatt, and you're gonna grab the hours provided, which is 6,200. Now we have the total, whatever answer it is, for our kilowatt hour per year, and our annual cost will be this answer. So we're gonna be writing it. Gonna be writing kilowatt per hour, and we're gonna be multiplying it to the rate provided, which is 0.14 cents per kilowatt per hour. Now you have the total amount you need. Okay, so that is the entire problem. So feel free to check it out. Pause the video if you need, or you can send me a message through my email if you're a little bit confused on something, So that is it. I will also post a video for the number 3, so the pressure of a truck tire. You can also check out my other video for the nozzle, so that's number 2, and how we're gonna be doing the energy balance equation on that one. Once you get the energy balance equation, you're good to go and you're good to solve. So say goodbye to Mr. Cowlin and see you on the next video.